So, you might wonder why I repeated the word power twice. Some multiples of non-negative power functions is because non-negative power is an adjective that applies to the word power. So if that confuses you, there is a reason for it. Okay? Okay, so, for example, x squared plus 5x plus 6. Okay? Because that's x squared plus 5x to the 1 plus 6x to the 0. So I've got integer powers 0, 1, and 2, and they're all non-negative, right? So those are the lowest integer powers, three lowest integer powers I could use. So that's quadratic functions, and if you know what we've been doing and practiced and so forth, you've got a pretty good handle on quadratic functions. And if you don't, you want to keep developing it, okay? Okay, so we have that. Example. This. A multiple of x to the fifth, a multiple of x to the fourth, a multiple of x cubed, and a multiple of x to the 0, which is constant. Okay? Easy to identify a polynomial. Okay? Not polynomial. That's not a polynomial, okay? Because square root of x equals x to the 1/2. It's a non-integer power, right? Okay, there are many other examples. Okay? I'm going to give you another definition. We're not going to do rational functions right now. But once you understand what power functions are, it's easy to understand what polynomial functions are, even though you don't necessarily know what to do with them. Okay? And we might as well talk about what rational functions are. It's a ratio of polynomials. It's a polynomial divided by a polynomial. Usually two different polynomials, because if it's the same polynomial, the result's just one and it's not very interesting. Okay? Polynomial divided by polynomial. And there are examples. there's a polynomial divided by a polynomial. Okay? They're quadratic polynomials, okay? And most of the rational functions we're going to look like involve linear or quadratic polynomials, okay? Or let's do that because that one has an interesting graph. Okay, but this one, okay? X plus 1 is a polynomial. It's a sum of x to the 1, it's a multiple of x to the 1, and a multiple of x to the 0, right? Okay? Or x minus 3 over x plus 5. When we study rational functions, which we'll be doing within about a week, at least we'll start with a simple one like this. And then we can move to these, and they're almost equally simple, except they're a little more complicated. Okay? And if we understand these and how to construct their graphs, we will be the first class in history that did. Individuals in the class usually understand. About half the class understands, and the other half some attempt. We really want to try to achieve an understanding of this because in the first place these functions can be really important. In the second place, the ability to apply the definitions becomes really, it makes you smarter. Okay? It's worth getting smarter. Okay? Gives you more aptitude for understanding graphs and trends and stuff that can be very important in most fields. Okay? And inescapable in many. Okay, so we're going to do this, and I'll tell you, now the graphs of polynomials all look like, well, let me draw you just some graphs of polynomials. Yeah, first of all, you could have a parabola, right? Okay. Now, you could also have something that looks like the x cubed function, right? So that's basically the x squared and the x cubed function. Now, once you do your homework, you'll understand that you could have a very flat parabola. That would be like dominated by a power function that has an exponent maybe 6. Because as we just saw, these things get flatter because of what happens at 1/2. They get flatter near the vertex. Okay? So that's like a parabola, that's like a flattened parabola. It just comes from the 6th power and 8th power, 4th power, whatever. Okay? And of course you could flatten this one. Okay? Other things that can happen. You could have this one, but it does this sort of thing. Okay? And we'll see how that arises. It's not too hard to understand if you know how to add functions, okay, graphically. But that's something that's still challenging, okay? We've done it. I didn't put it on the exam or the test, but something I expect to be able to do with arrows. Okay, so you might want to look back at that. But we'll be looking at it again. Or it could be like this. Okay? Or it could be like this. The thing they have in common is they're all smooth. And all these would be multiples of sums of positive power functions. Probably with a lot of them based on x squared, some of them. You know, this is like an upside down graph here. Starts way up here and goes way down here, but wiggles in the middle. Okay? Number of wiggles you got tells you things. I'm not going to tell you what that is. That's what they look like. And they're all based on these two shapes with some deviations kind of in the middle. Okay? So you want to kind of have that picture. You want to see what I'm talking about. And when you review the videos, you want to think about exactly what I mean. Okay? Okay, so. Okay, these are polynomials. Rational function graphs like typically look something like this. Now that doesn't look a whole lot like one of these, but what you got to understand is this is a vertical asymptote. And this is much like what you would get from a 1 over x function. Now it's kind of reversed because well, an upside down 1 over x function could look very much like this. So it's like you got an upside down upside down 1 over x. Except shifted over. So that might be 1 over x plus 3. Horizontally shifted -3 units. Right? If you take the 1 over x graph, which you know, it's like this in the first quadrant, like this in the third quadrant, right? Take the negative of it, well, that makes all your positives negatives and your negatives positive, your y values, and it makes it look something like this. And then you shift it over 3 units by doing a translation. Okay? And over here, this might be like maybe a 1 over x plus 5 squared. Okay? And those occur because, for example, x squared minus x minus 6 has zeros, okay? At x equals -3 and x equals, at x equals 3 and x equals -2, okay? So it's going to have vertical asymptotes at -3 and -2. Those vertical asymptotes are going to behave like translated and stretched basic power functions. Okay? Negative power functions. So you have to understand the positive power functions and the negative power functions. Then it's just a matter of being able to factor these or use a quadratic formula to find out where this one's 0 and where this one's 0. Okay? If this thing is 0, like it is at this point, that means that whatever this x value would be is 0 of the numerator, because that's the only way you're going to make it 0. The denominator can't make the whole thing 0 because there's nothing you can divide by to get 0. Unless your numerator happens to be 0. Okay? Just common sense. But we want to make sure it's common sense by kind of building it up. So that's kind of where we're headed for the next couple of weeks. Okay? Now, I'm going to talk about things you need to know how to do. Okay? Well, for rational functions, it just really comes down to being able to use a quadratic formula to figure out when this is 0 and when this is 0, and then use a little common sense. But we've got to give you the techniques for doing the common sense. Okay? There's more to it than that. That's kind of where it starts. Okay? Yeah, you can already do that. Okay? Which is one reason we try to develop these pictures before we dive into the details. Okay? And if you know how to use a quadratic formula, then this is no big deal. Now, there's a little bit of factoring involved, but factoring is almost never important. Okay? Except for understanding the structure of these things. So we're not going to emphasize the factoring, but of course I'm going to expect you to be able to do some basic algebra 2 level factoring. Okay? Something that people generally learn fairly well. One of the few things that our algebra 2 courses actually kind of teach people. Okay? Or at least so far it's appeared that way. Okay. So that's kind of where we're headed. Okay.